So in this lesson, what I want to explore is gravitation and specifically the motion of satellites around planets. Now, for this example, I'm going to use a satellite and I'm going to use Earth because it's sort of a tangible example that we can all sort of have some kind of understanding of what's happening here. So there are some aspects that we need to understand about the actual motion of the satellite. So the first aspect that we want to consider is that this satellite is going to be moving in an orbital sense. So it's going to be moving around the Earth like so. And what it will be based on is it will have an altitude. Okay, now the altitude and the radius from the center of the Earth are two different things. So when we consider the altitude is taken from the surface of the Earth, where the radius of the orbit is taken from the center of the Earth. So we must make that distinction, and you must make that distinction within your calculations. So what I'm going to ask us to find in this example is a couple of things. So we want to find the force between the Earth and the satellite. We also want to be able to find the gravity or gravitational force experienced by the satellite. And we also want to look at the velocity. So how fast the satellite is moving. So these are three key aspects. Now, what we want to think about is that this satellite is actually falling towards the Earth, but because it's got very little friction or other external forces acting on it, the way that it will fall will be in a circular motion. And we'll say that this circular motion is going like so, in this direction. Really, that depends on the way that we actually launch the satellite, so the trajectory that we put the satellite on initially. But it will be moving around in an orbit that goes around the Earth, and we'll be wanting to fall towards the Earth. And realistically, what happens is satellites do actually approach the Earth, and what they commonly have, or what man-made satellites generally have, is a little propulsion system that sort of tries to keep them in their orbit as long as they can. Now, for this example, we're going to obviously have to know a couple of values that we're going to anticipate. So we're going to say that the mass of this satellite is going to be 2.5 tons. So we'll represent it in kilograms, and we'll use scientific notation, 2.5 tons. Okay, it's probably the size of a minivan, is 10 to the 3, okay, 10 to the 3 denoting what tons would be. And the mass of the Earth, we're going to say, is 5.98 times 10 to 24 kilograms. Okay, that's a set thing. And we're going to say that we're going to set this satellite at an initial radius of 12 times 10 to the 6 meters. So that's about 12,000 kilometers above the Earth. Very high. Okay. And I'm just going to scrub all this out because we're going to do our working underneath. And the first thing that we're going to look for is we're going to focus on the forces that exist between the forces that are attracting the Earth and the satellite together. Now, think about it. The satellite is being attracted to the Earth. The Earth is also being attracted to the satellite. And the forces between that the two are attracted to one another, well, they're the same. But we're going to use Newton's law of universal gravity here. R squared, and we must remember that when we're working with Newton's universal law of gravity, that you really want to make sure that you're squaring your radius. So we're going to put in all our values here: mass of the satellite, mass of the Earth, and we'll put it all over the radius, and we have to make sure we square that. And the force that we get here, so the attractive force between the Earth and the satellite, actually comes out to, once we do our calculations, is 6924.75, okay, newtons per kilogram. So that's the attractive force that the satellite is being drawn towards the Earth. So the force here would be 6924.75 newtons every kilogram, and the Earth would be experiencing the same force moving towards the Earth. Now, the other thing that we want to investigate here is we want to think about, what's the gravitational effect that would be experienced if you're sitting on the satellite or if you're standing on the satellite. So as we all know, astronauts, when they're in outer space, they tend to float, and that's because of the lack of presence of gravity as we know it on the Earth. But there is still an element of gravity. So if we were, for example, a person on this satellite, the question that we're posing is, how much gravity would this person be experiencing? Now, we can find this two ways. Well, one way is we can say that F equals mg, and I'm just going to denote this g with an asterisk, and that just means that it's the relative gravity. And we know that my force was given by this. The mass of the satellite is 2.5 times 10 to the 3. And the gravity, relative gravity that I experience is just going to be 6924.75 all over 2.5 times 10 to the 3. And this gravity is given by as 2.77 newtons. And that's obviously, or newtons per kilograms or meters per second. Now that's obviously, just going back here, I've just made a little mistake here. This should be the force in newtons. It's not newtons per kilogram. But this should be the gravity that a body would experience on this satellite set at this radius from the Earth, or this distance from the center of the Earth. Now, there's another way that we can find this, and it's this law where we've sort of played with Newton's universal law of gravity, and we use the big mass. So this m value here is taken from the larger mass. And what we can say here is, if we explore this, times 10 to the negative 11, mass of Earth. I might run out of space here, but we'll see how we go. All on the radius. And we get our relative gravity being exactly the same. So there's just two ways that we can find it. Obviously, depending on the question type, you might want to consider which way you're going to use, which method you're going to use, but both are valid. Okay. So what we're going to say is that the gravity here being experienced is going to equal 2.77. And we just want to remember that value as we're going forward. Then the next step that we want to consider, so I'm just going to scrub this work out so that we can then think about finding the velocity. Well, how fast is this satellite moving in its orbit? And what we're going to do is we're going to refer back to our circular motion equations, and we're going to say that A equals V squared on R. Now remember, this gravity here, this is also an acceleration component, so we would normally express it as 2.7 meters per second squared. That's how fast the object is accelerating. So what we would do here is then we would say G relative equals V squared on R, and we can say here 2.77 equals V squared, whatever that value is, on 12 times 10 to the 6. V will end up equaling the square root of 2.77 times 12 times 10 to the 6. And this value comes out as 5,765.3 meters per second. So that's really, really fast. But when you consider the distances that it's traveling, it needs to be fast. And you got to also consider there's no external forces acting on this satellite. In outer space, we wouldn't consider any external force. Therefore, it's got no friction, which is slowing it down. All right, thank you.